In this video, we're going to look at the design of basic Cmos logic circuits. Each of our Cmos logic gates will have the following complementary structure. First, we have a connection to the positive supply voltage called VCC and another one to ground. Then we have our inputs, in this case two inputs A and B, a single output F, a pull-up network that connects the positive supply voltage to the output, and a pull-down network that connects the output to the low supply voltage or ground. The pull-up network connects to the supply voltage VCC, and it will be composed of only PMOS transistors, while the pull-down network connects to ground, and that will be composed of only NMOS transistors. The important thing is that only the pull-up network or the pull-down network can be connecting the output to one of the supply voltages at a time. So either the pull-up network is conducting or the pull-down network is conducting, but we'll never have both conducting at the same time, otherwise we'd short out our supply voltage. The pull-up network and the pull-down network, as we'll see, are logical complements. And again, the transistors we're using are Cmos, which means complementary metal oxide semiconductor. The first Cmos logic gate, which we've already seen, is an inverter. The pull-up network consists of a single PMOS transistor, while the pull-down network consists of a single NMOS transistor. If we have a low input, the NMOS transistor is open and the PMOS transistor is like a switch that's closed. Thus, there's a conducting path through the PMOS transistor to the positive supply voltage and the output is high. If we change the input to low, then the NMOS transistor is like a closed switch and there's a conducting path between the output and ground. Now we'll look at our first two-input Cmos logic gate. The pull-down network consists of two NMOS transistors in series, while the pull-up network consists of two PMOS transistors in parallel. If both of the inputs are low, then there's a conducting path through both branches of the pull-up network and the output is high. Note that the pull-down network, both switches are open, so there is no connection to ground. If I set one of the inputs to a high, I still have a conducting path in the pull-up network, and there still is no conducting path to ground in the pull-down. Same thing happens if I switch the other inputs. I get a conducting path through the other branch of the pull-up, but still no conducting path in the pull-down. On the other hand, if both inputs are set high, I now have a conducting path to ground through the pull-down network, but no conducting path to the positive voltage through the pull-up network. Looking at the resulting truth table, we see that this is the function for a NAND gate, not AND. Now let's take a look at a second example of a Cmos logic circuit where the pull-down network consists of two parallel NMOS transistors and the pull-up network consists of two series Cmos transistors. In this case, if both of the inputs are low, there's a conducting path between the output and the positive supply voltage, since both of the PMOS transistors are conducting or closed switches with low inputs. If we change one of the inputs to a high voltage, then the pull-up network opens up, but we do have a conducting path through the left branch of the pull-down network between the output and ground, so the output goes to low. If we switch both of the other input to be high, we still have a conducting path through the pull-down network, this time through the right branch, but since the bottom switch is open in the pull-up network, there is no conducting path to the positive supply voltage. Now if we set both of the inputs to high, we still have a conducting path through the pull-down network, this time through both branches, and no conducting path through the pull-up network. If we look at the resulting truth table, this is the logic for a Boolean NOR function, or not or.
If we wanted to design an OR gate, we could simply add an inverter to the output of a NOR gate.
Note how the output of the NOR gate feeds into the input of the inverter. Clicking through each of the combinations, we see that we now get the truth table for a OR gate. Similarly, we can construct an AND gate by attaching an inverter to the output of a NAND gate.